last one. Hopefully get through to the end of this one. I'm not sure if I will or not. Lots of maths in this one. Seriously, lots of maths in this one. Right, we did that. Coded all out what it was and what causes it. Okay, so the water gets closer to the screen, to the pump well, the velocity increases, so pressure drops and heat drops, and you get this cone that expands outwards, getting ever bigger through time. Will expand until equilibrium conditions are reached. They may not ever happen. It may keep expanding very slowly. Of course, as it gets further out, the area the water's coming through is much larger, so it's not expanding very quickly. Probably will continue expanding. Brilliant. Okay. So it's quantifying this cone, as I said before again, and getting some values from the creation of this cone, I've changed over time. That is going to give us our T, our S, and our K for the act of those really important parameters that we need to know for the groundwater modelling. And we just need to know then to tell us what our act is doing, how it's behaving, okay, and how it's going to behave in the future as well. And it's taking measurements during the pumping testing, okay, at predetermined intervals, at set distances from the pump well, okay, through observation boards that are constructed around it, that we get that information from. Okay, I'll talk about that as well. So we know these parameters here, all right, we know all those, and we get these ones during pump testing, the time of measurement since pumping started, and initially we started at small intervals because the change is very quick initially, and then we take the larger intervals through time because the changes get smaller and smaller while you're pumping. All right, there are various methods to apply to this data to quantify it, depending on the type of aquifer that we've got, and a whole lot of other parameters as well. There are dozens and dozens of different methods. I'll talk a bit about that as we go. Again, anyway, we want to get these here. So good. Right, okay, so this is what I was talking about before. Here's an observation bore, set distance away. Of course, I can't move. That's R. B is aquifer thickness. Q is the discharge, the amount we take out. That's constant. So that's constant, that's constant, that's constant. Those are three things that don't change through the pumping testing or through the when we start taking water out of the well permanently. This is what does change. Originally the surface was up here, the mesometric surface, okay, the water table of the scriptified aquifer. Once we start taking water out, that drops. In the well itself, it drops the most. Okay, outwards from the well, it still drops, but it drops more slowly. Okay, and to a much lesser degree. The further away you go, the less it's affected. Okay, and what we're measuring during the pumping testing, just predetermined time intervals. Okay, this here, drawn out, yes. Okay, and now the difference between the original water table and the static water level, sorry, the water level of mesometric surface within our multiples which intersect it. Okay, so H0 minus whatever H is. Okay, we measure it from the surface. You don't need to go H0 minus H. Sometimes it's quantified as that. We'll just call it drawdown. It's S. Drawdown is when you take the water out and the well is dropping. When you stop pumping and the water level goes up, it's not called draw up, it's called recovery. We'll talk about that later as well. Oh, there you go, step test and recovery. So the first thing you do, what you should do anyway, when you start, before pump testing, you're starting to get into the nuts and bolts of the thing, is to do a step test and then measure the water level at different pumping rates and then the recovery within the well. You can analyse that and give you an idea of how well your well's going to perform and what the maximum rate you may be able to pump it at during pumping testing, hopefully confirming the amount you want. Right? Because if you really want to test your aquifer properly, you want to test it at the rate you want to get water out of it. Okay, in the future. And this will tell you if you can do that. You may not be able to. Sometimes the calculations are wrong or things are different and you have to reduce it. But either way, a step test will give you an idea of what's going on with your aquifer. There are various ways to analyse it. Okay, generally you don't go overboard with it because the pumping testing and long-term stuff is much more important. So you pump the well at increasingly high discharge rates for set duration, maybe an hour. Okay, at a low duration, at a low discharge rate, maybe double the rate for another hour, double for another hour, double for another hour. Okay, and you get a curve that looks like this. You can see when you first start pumping, or you first increase the rate, the level drops quite quickly and then begins to level out. Okay, 2, 3, 4, 5 steps for this one. Then you turn your pump off and you measure the rate of recovery within the well. Also, you can do things with this data. I'm not going to worry about it here because it's not super important in the context of what I want to teach you. But you can actually analyse each of these steps and get some of those things I was talking about, T's and S's and all that, and maybe quantify what's going on in your well. Okay? But they'll only give you preliminary results because you're only short-term pumping. Each of these steps is only an hour, so they're not going to tell you a lot about what's happening overall for the aquifer. But if you're not, your cone of drawdown isn't extended very far outwards. Okay? This hasn't established itself. Constant rate testing, sampling and recovery. This is the important bit. So pumping, taking water samples early on in the pumping regime, maybe middle and then late to see if any changes through time in water quality. And once you turn your pumps off, measuring the recovery within your well and within the aquifer as well. So data from this and this can be analysed to give you values for TS and K. Okay, we'll talk about those various methods of doing it. And you should do as many of those as you can. Okay, get as much information as you can from your pump test. You only get to do it once. It's expensive. Okay, it takes a long time to set up. It takes a lot of effort to monitor it and control it. And it's really important that you get good data. Make sure you get good data and then do something with it. The maximum you can with it. This will establish our properties. Okay. So in this case, we turn the pump on at a constant rate. We don't change the rate at all, it stays on the same rate. Okay, it's got to be monitored. Make sure it does stay at the same rate the whole time. Preferably, like I say, the rate we want to eventually get water out of the well, that would be good. Sometimes it's not practical because pump test contractors sometimes don't have very big pumps. Okay, sometimes the pump you're going to use for your final installation is very big. They don't have a big pump, and so you have to reduce the constant rate discharge. But if possible, you want to do it at the rate that you're going to be taking the water out. The longer the better. Okay, if you can do 2 or 3 good pump tests, that's awesome. Again, sometimes the cost doesn't allow that. Okay, but you certainly want days, but preferably weeks. Okay, the longer the better. It's really good. You do that. You're going to be monitoring water levels in the pump well and the old spores, as many as possible. Okay, some existing old spores, so those people's wells that you've talked to before, you might be able to use those, see if they're affected. You'll have constructed some yourself as well. But you've got to analyse all that data to better quantify your aquifer. The aquifer is probably not homogeneous. Okay? It's going to be different in different directions. So if you've got data coming from different directions, it's really, really good. So you're going to record time versus drawdown data. Okay, initially at 30-second intervals. Then we move to 1 minute, then 5 minutes, then 10, 30, or whatever you've decided. Okay, that program will be set down in the contract for the contractor to follow. But early on, you want short intervals because that's when the biggest changes happen. That's when things really start happening. Okay, after a while, things start to even out, maybe even equilibrate in the short to long term. Don't stop recording when you turn the pump off. Right? You record the opposite here. You record recovery. So water levels in the well recovering, water levels in the aquifer recovering as well. You need to consider how you're going to monitor your pumping test. Okay. It's very important that you don't just have, or if possible, your pump well in one old spore. You need several, and preferably at varying distances away and in different directions away from the pump wells. If you have a pump well here, you have one, a couple right angles to each other, but different to 25, 50, 100, 200. That's just an example, and it will depend on what land's available and how you can spread the things around and how much you're going to spend. An unideal situation is just to have a pump well and one very close by old spore. One old spore is okay, but it needs to be a bit further away. 2 or 3 are better. If you can only have 2, put them at right angles to each other. It makes much more sense than putting them in a line. But it may depend on other things that you've discovered during your study as well. Okay, it takes a bit of experience to lay these things out, but the more the better. You need to be sure that the rate of discharge out of the well is constant, not change. That'll affect your calculations quite wildly. Okay, constant. Otherwise, things become intensely complicated. You can't really do anything. You can measure that in various ways: flow meter, orifice meter, rectangular, notch. We use all sorts. The pumping contractor will have one. They'll have to give you calibration certificates to let you know that it does indeed accurately record the discharge rate. And basically, the pump test contractor will live on site the whole time this is going on, because he needs to be there in case anything goes wrong. Okay, if the generator dies or the pump dies or something, he has to be there to sort things out really quickly, because that effectively ends the test. He has to wait till everything recovers and start the test again, because the contractor will call for a specific length of test, and it has to be done if they've signed it. Water samples will be collected during the pump testing, okay, preferably early on, okay, maybe a few hours to a day after you turn the pumps on. It'd be nice to get some in the middle, but definitely just before you turn the pump off. Okay, then you'll be able to see some trends, decreasing trends or increasing trends and nasties that you've discovered or whatever But you want to make sure, you've got to make sure that the water is acceptable, and if there are issues with it, they'll go to the client, because then they'll need to plan how to treat that water and get rid of those issues when they start using it for account supply. So different types of flow meter. This one just extracts on the outside, okay, and eventually measures flow through a pipe. But then also these more manual types of the orifice where there's a tube of a set length and it's got a hole at the end of a certain diameter. You know that length and that diameter. You can calculate the rate of discharge coming out of the end there, okay? And you've got a thermometer up here, and once you get it to a certain level, you know what your discharge rate is. All you have to do then is make sure, check periodically, that the water level in your manometer is staying at the same level, and you know that you've got your required discharge rate. So nice and simple, okay? Simple mechanism that works really well, and it's cheaper than buying a flow meter from many contractors. So it is the caravan that these guys that were doing one of our companies lived in. They were very strange people. They used to do this for a living, and they were really good. But they did a good job. And there's a weir, same sort of thing. Water flows from the well and through this weir, and the width of the weir is set, of course, you know that. You can measure the height of the water coming over the edge of the weir a certain distance back, or the height of the water within the weir, okay, and calculate what your discharge, or calculate what your discharge should be for a certain height to make sure then periodically that the water is always a certain height within that weir. You've got the same discharge going on. Again, simple devices, okay, but they have to be calibrated and proven to work, otherwise you can't use them. You've also got to control the discharge of the water coming out of the well. You can't just spray it all over the place, because you're doing this on someone's property or near someone's property or whatever. And someone's getting all the water out of these things. Okay? You're pumping crap loads of water out of these wells, and you've got to get rid of it. Otherwise, you can get in trouble. And these guys went to quite a significant amount of effort to get rid of it, because the road is way over here, and we're in the middle of this paddock doing this pump test, and so they snaked the tube all the way down and we discharge it off the road down there, which is okay. We had to get them to move it a little bit, because this is someone's driveway, and they've been constantly splashing through water for 2 weeks, but overall they're doing a pretty good job. And it's not, so again, it's something you check on. It's why you do site visits, okay, to make sure that these things are working. It's all very important. Keeping public relations good is a good thing when you're dealing with these sort of situations. So this is the data. Well, this is the graph of the data you get. Okay, you get the tables and tables of the data, and you reduce it down and you graph it. This is a linear plot. Draw down here, the S down here measured. Okay, so short time intervals to start with, and longer time intervals as time goes on. And time across the bottom here, I graph these ones in seconds, because that's what we were calculating anything, and it doesn't really matter as long as you keep your time constant to all your calculations. You can see initially, over a very short time period, the water in the well started with 0, okay, and then we reduced it to proper RL, and then it goes, takes a big dive, and when that's happening, you're sitting there holding your breath, hoping it doesn't keep going, because then you're stuffed, because your pump will shut down and you've got issues, you're not getting enough water out there. A new plan of attack, hopefully things still work. But you can see over time it levels off, and then almost equal breaks. It'll just gently just carry on over time. So that's really good. That's what you want. If you get that, you're happy. Okay. You've got about 30 metres of drawdown in your well. That's quite a lot. As long as you've got a pump that can handle it, it's okay. It may be a little bit inefficient, but either way, you're okay. Everything's going nicely. Okay. Of course, you stop the pump test here. So you don't know if here it's going to go again, but judging by this data, you look like you're doing pretty well, okay, if you get that kind of data. Because when you switch the pump off, you get the opposite. Okay, the water in the well starts recovering, and recovers. Probably never ever get back to the original level. If it does, it'll take a heck of a long time. Okay, the water's going to compress that aquifer. You can see this is 1 week at 20 litres a second, and recovering 3 days almost gets it back to normal as well. And that's the data you want. Drawdown data during pumping testing. Recovery data after pumping testing stops. So this time here is the time since you turn the pump off. This time here is the time since you turn the pump on. It's important to make a distinction between those, because that will come into our calculations later. Then you analyse the data. This is the fun bit. I'm going to go into the background of some of this and show you bits behind it, the bits the computer programs don't show you. It's important to have an understanding of how it's done, okay, rather than just pressing a button, because some programs will give you strange results or errors, and if you don't know what parameter to go in and change to fix those errors, or how the program is working, how it's actually giving you the output data, then you're really just wasting your time. Okay? So it's really important that you actually have a little bit of an idea what's going around in the background, what the computer's actually doing to give you the data. Okay? I'm not hundreds of dozens of methods for analysing Pupty's data. Your computer program will give you a whole list of things. It'll give you all sorts of different people's names and dates that have come up with different means of analysing data from a whole different range of conditions, because it'll depend on the type of aquifer you've got. Right? Whether you've got confined, unconfined, semi-confined aquifer, the conditions reached during pumping, whether they reach equilibrium, right? Whether they're transient, when you turn the pump off. Okay? The type of test conducted, so whether it's a step test, whether it's a constant rate test, whether it's recovery data, okay? All those kinds of things. Whether it's a long-term or a short-term test, whether it's early or late-time data. And there's a whole range of different analytical methods that can be applied. Okay, so all these things here, there's a whole range of things. All of the methods make assumptions. They have to, because these things are exceedingly complex. Okay, groundwater flow equations are horrible, nasty things, and there's so many variables. You've got to make assumptions. You've got to simplify things. Okay, it's a natural system. You can't mathematically quantify it exactly. And most aren't strictly true. It doesn't matter overall. Long term, it doesn't really matter, but you've got to be aware that there are assumptions that are made. So a few methods you may encounter if you ever get into this stuff. Tice, he's a famous one. Jacob another. Okay, for unconfined aquifers, there's 3 common methods. Then you can find there's another 3 common methods. Confined aquifer, another. He's got several for confined aquifers, a couple for that. Unconfined and confined aquifers are very different to calculate for, because in an unconfined aquifer, as you pump, the aquifer starts draining, and so the aquifer thickness, essentially the saturated aquifer thickness changes all the time. Right? The amount of the aquifer saturated changes to take water out of it. In the confined aquifer, it doesn't, because the confined aquifer is always saturated. The piezometric surface drops, but the aquifer thickness is always saturated with water. So these things are really powers. You go through one of these with you, because these are the ones you should be targeting most of the time. But either way, the people have done all the hard work for you. They've developed all the methods and whatever, and the background stuff. And so essentially what you guys will do is start up your program, put your data in, push a button, and it will give you an answer. But like I say, if you don't know what the answer means or how it's achieved, you're not really doing your job. And there's even methods for fractured rock aquifers, which are famous. Anyway, it's just the way it is. So we're going to deal with flow in a completely confined aquifer under transient, so non-equilibrium conditions. When you turn the pump off, the water level is still dropping. Okay, so just pretty much normal state of affairs for most confined aquifers. Hopefully the water's not dropping much, but it will still be dropping as you pump if you lift your pump on. And we'll use Tice's 1935 method. He used the technical files. Actually, he didn't solve it. It was a friend of his who solved it, a mathematician friend who sort of helped him. And he tried to credit him for it. The mathematician guy goes, "Oh, that was easy. I could do it in my sleep," and just didn't want anything to do with it, which is quite spectacular considering the nastiness that went into it. It's pretty hard stuff. But anyway, he applied assumptions. As I said, they've got assumptions for these things. The water is confined top and bottom. There's no recharge. The aquifer is compressible, and the water's released instantly as soon as you start taking the water out, and you've got a constant discharge. So they're pretty safe assumptions. They're not such a big deal. But you've never got that recharge. In fact, you want recharge. Recharge would be great. You start taking the water out, water comes back in from somewhere else. You've got more water to use. It's all really good. But either way, this is one of the assumptions they had to make, or you have to make to get these things to work. You express the transient drawdown as S, that's that S value I talked about, as this. So S equals any particular time that. There you go. Pretty simple stuff. Everyone loves integrals, I know. It's fantastic. So there's T, transmissivity, is one of the things we want to work out. We don't know that. Q we know what fault pi is. And we don't know anything about this here, and we want to get drawdown. Okay, so we want to get this at a particular time. Luckily, we can deal with this, okay? The U here equates to this particular formula here, S being storativity, transmissivity, T, particular time. Okay? But this here can be approximated and dealt with by doing this. It just gets better and better, doesn't it? Okay? Don't worry about it. You don't have to reproduce any of this stuff, but this is just what they were doing. It's all based on heat flow equations, and they did a jiggery poker around to make it work with water. So this is called the well function, and it's abbreviated WU, okay, which is pretty good. And so you can actually change this equation here, get rid of all this, just call it WU, because very helpfully, this guy called Wenzel in 1942 went laboriously through and conveniently tabulated WU for a whole range of U values. Thousands and thousands of damn things. He must have been really bored, but it was really good that he did, because now we don't have to do anything nasty like this. We can just use this equation instead of all this crap. Remember this, we're going to use this later, and we're going to use this later as well. But anyway, that's what he did. It was really good. Okay, so you can rewrite this thing as this, because we want to work out what T is. Okay? We want to work out transmissivity. It's one of the things we want to get from our aquifer. Okay? We're going to know what this is a variable. We're going to have to find out what this is. And this is a variable. We have to find out what this is. But we're going to do this by a little tricky graphical method that Tice worked out, which is what your computer does in the background. All right? Which, if you stuff up a particular part of, or don't know how the computer set it, will give you errant results or error results, and it'll drive you mad if you know what's going on. And some customer says to you, what's happening? You haven't changed the match point, and they don't know what you're talking about, so is why I go through this here. So T transmissivity, one of the things we want to find. We do know what Q is, that's pretty good, but that's all we know here. And we can rewrite this thing here, use that. So we get storativity, which is one of the other values we want to find. We also want hydraulic conductivity, but that's really easy because that's simply transmissivity divided by the aquifer thickness. Remember, from one, I see ages ago, the transmissivity equals hydraulic conductivity times B, the aquifer thickness. I hope you should know that, so we get that easily. That's the easiest one to find out. But first, we need to establish T, because we need to get that to put in here. But we also need to find out what U is, what little t is, time, and what WU is as well. And there are some clever jiggery code we can use to do that. Okay, so if you rearrange these and log them, we get that. And that, you're thinking, well, what's worse? What's the point of that? The log is equals log function plus this, and log t equals log 1 over u plus this. Notice that this and this are constants. None of the values in here change during our testing. Discharge is always the same. The transmissivity of the aquifer doesn't change. It's constant. Okay? It'll be through time. The distance between our plug well and our measuring point doesn't change. Storativity doesn't change. Okay? It's a constant of the aquifer. Okay? And then there's transmissivity. So this here, this log function, and this log function are constant. So essentially, we've got log s equals log w plus a constant, and log t equals log 1 over u plus a constant. So what you can do, if you graph log s against log t, okay, on a log plot, and then that's your drawdown data, and that's your time data, that's the stuff you get from your pump testing. Okay, so we've got that information. It's very easy to address the axes, and Excel was cool, take about a second. And then if you can make a graph of log WU, the well function, against log 1 over u, okay, which our Fred Winston did for us already, he's already given us those numbers, right? You should get two graphs that are very similar or the same, right? But they'll be offset horizontally and vertically by these constants, okay? And that's the basis behind what's called the curve matching method to work out Ts and K for a confined aquifer. This is what your computer will be doing in the background, that you'll be able to see it, okay, as you try and get your calculations correct using programs such as aquifer test or whatever. And you can solve, if you can get value for T, a value for S, a value for WU, and a value for U, right, then you can plug those into here. There's this one and this one, and you can get those, okay? So this is the type curve using all those numbers that Winslow crunched of WU for various values of U, okay? Of course, it's invert U to 1 over U, log plot, okay? So log plot on both axes, and it makes a nice smooth type curve, an ideal curve. You have the ideal conditions, and you pump something, you should get a nice shaped curve that fits somewhere along that one, okay? Never really works perfectly like that because we deal with natural systems, but that's not what the really best fits, okay? Here's a graph of drawdown versus time. Don't worry about things like FIFA, but these ones out of the book, this is original data. Working with original, useful, and real life data is much harder to explain, so it's much easier to use book examples. And so we've got a nice curve as well. Okay, you'll be able to match this to part of this along here somewhere. Okay, and when they're matched, the two will be offset horizontally and vertically by whatever those constants were in that log thing that I showed you before. And that works really, really well. If you've got good data, it works perfectly well, as long as you've got the right conditions. So here's the two overlaid. Here's our type curve. This one here, this nice one here, 1 over u against WU, log plot. This here also is a log plot. There's our drawdown, that's S. There's our T, little t, time, in minutes, days, seconds, whatever you want, as long as you keep it constant, as long as you're aware of what it is. As you can see, this pump test data fits nicely along this part of the curve. Okay, just here. But the two graphs are offset, okay, by a bit of a margin. Right? Well, that's really useful for us. So what you do is you line the two up, make sure to keep the axes parallel. Then you pick an arbitrary match point. At any point on the graph, it doesn't matter if he's going to stick a pin in there or whatever, make a point. Alright, and you can see from that point, you can get a horizontal line that intersects the drawdown axis at a particular value and intersects the WU axis at a particular value, and a horizontal vertical line that intersects the time axis at a particular value and intersects the 1/U axis at a particular value. Do we need those four numbers for anything? We do know we need a value of S, little s, a value of little t, a value of 1/U, or U, and a value of W to go into these. Right? That's how you can get them. Pick your match point, right, so that 1/U and WU are whole numbers. And if you can do it so that they're both one, it makes things even easier for you, especially if you hand calculate it. Okay, because of course the ones just get rid of themselves from the equation. But anyway, if you look here, you can read off values for T, okay, for S, for WU, and for 1/U. Then it's a simple matter of inserting them into those equations, and it pops out an answer for transmissivity, for storativity, and for hydraulic conductivity. Now, of course, the computer's doing this in the background. What you'll do is you get a type curve on your screen, and your data pops up, and you can use the arrow keys to move your data against the type curve, right, around, and the computer will constantly spit out numbers at you until you decide where the best fit is, and it'll stabilise on the capital T, capital S, and capital K that you need, okay, that you use to try to quantify the aquifer. But if you, sometimes, in matching your curve, sometimes the curves don't match very well, it's very hard, or they match way up here or way down here. Alright? And if you set your match point in a particular thing, like let's say 411 here, and you go through and it moves way over here or way down here or something, the computer has a hissy fit because it can't make a calculation, so it comes up error. And people get very frustrated because they don't know how to fix that. But there is a parameter in your program where you can go to change the match point to make it so it sits on the graph. Again, it's one of the biggest errors that people make with this, and the problem is that they then go and use the data that's erroneous. Anyway, substitute those to get T and S. So there we go, there's our T, so we can get transmissivity, Q over 4 pi S times WU, okay? And once you've got big T, we can substitute here as well. We've got big T, we've got a value for U, just a little bit of that, okay? And we've got a value for T, we know what that is, we get our S. And of course, divide T by B, and we get K. Done. Easy. There you go. It's as simple as that. Don't say computer will do it all for you, but you do need to have A, good data, B, a decent match for your curve. You also need to know the aquifer you're dealing with, okay? Because there are many different methods depending on the aquifer. So if you're not sure, if you think you've got a confined aquifer, if things aren't working really well for you, or you're getting a curve that's not matching very well, or the shape's weird or something, you may not be dealing with a confined aquifer, maybe a leaky aquifer, which will behave very differently. You have a different set of calculations for it. And this is just one way of doing one set of calculations for one particular example. Okay, but again, like I say, it's all computerized. But this is what the computer's doing in the background. That's what you need to be aware of. There are other ways. Here's another example. If your pumping has been going on for a long time, and if your ox bore is quite close to your pump well, then that U value becomes negligible and can be actually discarded, and the equation can be rewritten to some degree. Okay, so you get something looking like this instead. And when you play with this and put your values on code that you use a semi-log block this time, okay, you can get a nice straight line, and you can use this to get these two equations, which is slightly different to the ones I said before, right? And you can analyse it in a different way. Again, your computer will show you this. You put the line of best fit through. You've already programmed your data in. There's no type curve this time. Okay, this is your data. Okay, this is the log scale for your time, but a linear scale for your drawdown, for your S. And you can put a best fit line through that. Okay, you can get the slope of that best fit line. The slope equals one log cycle, so it'll be between 10 and 100. Okay. Move it over a bit, it will be between 100 and 1,000, doesn't matter. So the difference in drawdown between here and here, that value, okay? And again, you can slot that into your to your equation to get your result. This here, whether your line intersects the time axis as well, okay, using that too, you need T0 for this one. So there's your delta S, one long cycle, that number there will slot in here, solve for T goes there, T0 value from the intercept up there. Okay, so a different way of analysing it, but a different situation. Okay, a very, very long-term pump test with an OBS board that's reasonably close by. You can apply both to the same set of data to see it's giving you consistent results. That's good. If they're not too different, it's all good as well. Okay, things are working okay. And then again, of course, K is the easiest one to get because it's simply dividing it by aquifers. Sometimes it's not that easy because sometimes you get into an aquifer, you've drilled 200 or 300 metres, and you get into it. You have no idea how deep it's going to go. You can't go any further. It's quite a good aquifer. You don't really need to go any further. So you actually know what B is. So sometimes establishing K can be really tricky. You've got to make some sort of estimate or guesstimate possibly or whatever. Okay, but it's important that you establish some value of K because it's one of the most important parameters for the groundwater modelling, which I'll hopefully talk about in a minute. You can use the residual drawdown data as well. Okay, so the recovery data. This residual drawdown, so once you turn your pump off, you can use that. It can give you T and K, some cases, sometimes it can give you less, sometimes not so good. Okay, so you simply plot your calculated your recovery data, okay, so the difference between the original water level and the water level rising, and this is the time since pumping stopped. And again, notice long scale, linear scale, fit a straight line through it. One long cycle gives you the slope of the line, in this case that's your delta S minus S dash, which you need. Okay, slightly different equation here again. And your intercept here, giving you your T0. So same sort of thing. Okay, and again, K by dividing 2 by B. It's all good. Okay, so don't neglect any data. Use it all and analyse it, and use some different methods to analyse it and see if it's making sense. Wildly fluctuating results, you need to go back and look at your aquifer, make sure you're dealing using the proper analyses for the aquifer that you think you have. Otherwise, you don't have to reevaluate your what kind of aquifer you're dealing with. Okay, and another method doing the same thing. This time you use your residual drawdown and the time since pumping started over the time since pumping stopped. So another way of analysing your data, getting more information out of it. Again, it's linear log. Okay, straight line, one cycle gives you the delta S you need. Right, and simply plop it in to get your data. You can't get stored activity this way on your transmissibility, but you can get your hydraulic conductivity as well. When you look at your data, when you're plotting it, before you do anything with it, the shapes of your data on a log and semi-log plot can be quite indicative of the kind of aquifer you're dealing with. They can give you an idea of what you're dealing with to start with in a lot of situations. Not always, some situations are complicated. Fractured rock is one that's just nasty. Right, but if you've got a nice confined aquifer, you can see, these are turned upside down from what I showed you before, so it's drawdown, it's going up this way, right, and time that way. On a log plot, you get a nice curve. It fits that Tice curve perfectly in an ideal situation. Okay, that typifies a confined aquifer. On a semi-log plot, so linear drawdown that way, and then it just goes up and it becomes a straight line. But each different situation can give you a slightly different curve. You see this leaky aquifer here, goes upwards the same as here, but then it tapers off and becomes horizontal, so we've reached equilibrium conditions because the leakage into the aquifer is replacing the water that you're taking out over time, so that works out really well. Same for consolidated ones, okay? Now these aren't gospel, okay? They're idealised conditions, but when you first graph your data up, chuck into Excel, push the go button, draws the graph for you, even just a quick glance can give you an idea of what you're dealing with, and confirm what you thought you were dealing with from your field results, hopefully. You can also calculate your well efficiency from distance drawdown plots. You know where your pump well is, and of course you know exactly how far away all your OBS bores are, and you know water levels within them at a particular time. Okay, so this is distance in the log plot here, and drawdown in your pump well, okay, and your OBS bores here. Now, theoretically, of course, this is the outside of the casing, a very small distance from the centre here. Theoretically, this a straight line, that should form a straight line through all these things. This is a log plot, and this kind of drawdown was curved. And where it intersects your casing on your graph, the water level within your well should be there. Of course, it's not, because wells aren't 100% efficient. For various reasons, water coming in from water flowing up, you get friction. Okay? you get energy loss through that. You get rapidly flowing water, you get energy loss through that. You get turbulence as well sometimes, it's the energy loss, and so the head in the well will be always lower than theoretically it should be. Okay, so in this case it's way down here. There's not much difference. The smaller the difference between the two, the better. It means that your well is more efficient. Okay, that's what you want, an efficient well. It's less costly to run, it uses less power. You may be able to use a cheaper pump to get your water out of it as well. Okay, your efficiency is your theoretical drawdown over your actual drawdown, and the larger, the better. You want a well that's more than 70% efficient. If it's anything less than that, then you're really struggling. But there's a whole lot of things that have an effect on whether it will be efficient as well. Whether you've chosen your screens properly, remember screen length, whether you certain amount of open area to keep their velocities in between the 9.03 metres per second, etc. Casing diameter, velocity through casing, whether you can use filter packs, okay. And the penetration in the aquifer is also important as well. Partial penetration leads to well efficiency. Okay? When you construct your well in your aquifer, you haven't got all the way through, you've just used the top part. So the flow lines are bent, and so the water has to take a longer path to get to the well, and so it needs to go faster and faster and faster to get there. And the more faster it's going, the more energy it's losing, the more inefficient your well is. Okay, so you can see the effects of partial penetration. The flow lines are always bending to get water from the parts that are away from the screens to the screens. There are some ways around this. If you don't, well, you may only have a certain amount of money to put screens in. Screens are prohibitively expensive in some cases, especially those VY ones I talked about. You may only have money for like 20 metres of screens, your aquifer might be 60 metres thick. So you can do something like this to make your well more efficient. You can break your screens up, because the casing that goes in between them is very cheap. So you can break your screens up into various lengths, okay? So you have basically lots of small screen areas all the way through, and you can see the effect that has. You don't get these big bendy lines here, you get straight lines. That will improve your well efficiency. Okay? You could also, of course, screen the whole thing. That will improve your efficiency markedly. But either way, the efficiency is important. That's why I think you can look at. Not really seem to ignore it, but it's quite important. Okay, testing, water quality. We need to know if our water is going to be drinkable when we start taking it out permanently. Initially it might not be so. We've developed this well, so there's still stuff in it. There's still a bit of filter cake, there still might be material left in there from the drill and all sorts of bits and pieces. So after the first maybe day or so, you can take water out and collect it. Along the lines that I said earlier, it'll be in specialised bottles. The people at the labs will deliver you on this sort of bottles, especially to collect water in, some different chemicals, all sorts of things. Should be kept at constant temperature, preferably at the fridge. If you want to know what the water temperature is in the bore, then measure it as it comes out of the ground. Same with the pH, measure that as it comes out of the ground, because that'll change through time. All these other things that you just seal it up in a bottle and send it to the lab, and they'll do various tests to tell you what they are. But earlier on, when we were doing our initial testing, we just tested for a small suite of elements, because we're just interested to see if the water was possibly drinkable, right, and wasn't near the sea or near a hydrothermal source or something like that. Okay, that's all we did initially, and it went for a food. Now we want to really test it. There's a whole range of things, because of course the New Zealand health standards for drinking water are quite stringent, and you can't feed water to the public that doesn't conform to those standards. Well, in most cases, I suppose. And so you take your test and you sort of say, test it for a full suite of compounds, lots of things. You test them for dangerous inorganics, organics, all sorts of things, a whole range of stuff, 100 things positive. But the more important ones you need to be aware of and what they do are things like iron, Fe2, Fe3+. And of course, water leaches stuff out from rocks. Iron and manganese are two of the big things that leaches out. These, of course, when they flow through pipes and into your whiteware in your house, stain things quite a lot. And iron precipitates out and coats surfaces. And of course, people don't like that. They don't like their things being stains that look bad. It can even stain your clothing and things in washing. That's pretty bad as well. It can also encrust pipes, okay, and screens. It leads to well efficiency very quickly, and it favours bacterial growth, which you certainly don't want, and also some of these bacteria, they grow these sort of gungy, cloggy, filmy type stuff, which clogs up your well too. But this kind of stuff can be treated quite easily. Iron and manganese can be treated during aeration in your treatment plant. As the water comes in, you aerate it, and the stuff just precipitates out. So that's not too hard to get rid of, but you do need to be aware of it. There's lots of it. They'll have to plan for that in the water treatment plant down the road. Silica, dissolved silica again from rocks. In warmer waters you'll be able to dissolve all this stuff, and of course it precipitates out. okay, when the water flows through the screens and the velocity increases, pressure decreases, and encrusts quite nicely as well, so it's something to deal with.